Hey everyone, this is the optional assignment for ME577. Today we're going to focus on design for extrusion. My name is Mihir Nadig. I'm a engineer, a medical device engineer, so I thought this was specifically relevant to me, and I would be able to provide both some insights based on research as well as some industry experience here. So what I'm going to cover is an introduction and overview. I'm going to cover the main design variables when you talk about catheters, or in this case specifically extruded-based catheters. I'm going to talk about the manufacturing processes. I'm going to talk about secondary operations, then finish up with general design guidelines, cost factors, and references. So to start off, the main reference for this presentation is the Catheter R&D Handbook by Damien Carr. This is relatively new, really a wealth of information, as well as information on prototyping specifically, which is a reference that has been missing in the device industry, medical device industry. So I'd really recommend it if you have to prototype a proof of concept or something similar. Okay. So to start, what is a catheter? It's a long, flexible, hollow cylinder used to gain access to inside of the body. It's made of medical materials with varying levels of biocompatibility. So specifically, catheters are extrusions that are made for medical devices. Hence, a lot of the information in this presentation is going to be specific to medical devices. Some important terminologies that I'm going to call out are lumen. So lumen is an internal channel. So if you look at a cross section, which I can draw, it's just the inner diameter, if you will. And multi-lumen is a catheter with multiple internal channels. So as we'll cover, you can have cross-section areas with multiple lumens, and the geometry can get quite complex, which is quite cool. So catheters overall can be classified into three categories according to Carr. So first, short-term catheters. These are catheters used from 20 minutes to 4 hours. Sometimes they can be reused with sterilization. So a big thing with catheters and with medical devices that go into the body is that they need to be fully sterilized to be used, and that lends itself to a material consideration when choosing materials for medical devices. The next category is long-term catheters. So these are catheters used from 2 weeks to 3 months with the possibility of extended use. They're often more flexible to compensate for any movement or any shift in the anatomy. A common one is catheter for urine. And then finally you have external catheters, and these are catheters meant to be worn over the anatomy. Another example of a urinary catheter here, they can be used for a few hours to a few months depending on the patient's needs. So a measurement system that's important in catheter terminology is the French system. So they don't use standard inch or millimeter definitions when you're talking about the external diameter of the catheter here. So an example is shown here of the equations to get there, but just to drive the point home. So if you have the exterior dimension of, let's say, 9 FR, it's shown here. What this actually is 3 millimeters. So divided by 3 equals 3 millimeters. And so when you're looking for an off-the-shelf extrusion or speaking with supplier companies, you use this French system, and there are multiple charts available, or this as a guide to how to derive the French system. It's also key to use French sizes for your interface components. So for example, if you have a collet that comes around this, you want to size it for a standard French system in case you need to switch catheters down the road. Okay, so now I'm going to cover functional requirements. These are things you need to understand before designing your catheter. There's some intricacies and some caveats that come up when you're designing specific to medical devices as well. So this is what we'll cover now. So the first one being making sure it's recording. First one being pushability. So often you have a long length of catheter and you need to push it on what's called the proximal end, which is closest to patient, and it needs to translate on the distal end. So that's something you have to understand. Column and radial strength are pretty self-explanatory, same with stiffness. Bend radius is a nice one to focus in on. So bend radius is the tightest radius that the catheter can bend, pretending those are the same. And it can be measured at 180 degrees or 90 degrees as I showed. Yes, that's an important variable to consider because it usually is driven by which areas of the anatomy that this catheter needs to access. Training recoil, force translation, flexibility, kink resistance, this as well ties into bend radius. So here you can have it kink when you try to bend it too far. This is often two driving forces in designing a catheter from my experience. So diameter or run out tolerance over the length of the catheter, especially as you have longer and longer catheters, you want to make sure you know what tolerance scheme you need to be in. Steering response, so sometimes you have tips of catheters where they'll actually be able to move the end based on internal guide wires that are pulled. Duodenoscopes are a common application for this. And so understanding that. Durability, lubricity, this is a big one as well. So both internal to the lumen and external on the catheter, but let's focus internal on the lumen. If you're pushing a component through or translating a component inside, especially when bent, so up here, if you're pushing a component through, you want to make sure the component can translate smoothly or to some force requirement. So that's something to be considered. Biocompatibility and then radiopacity. So this is the split requirement, and what this is how compatible it is with human tissue and the human body in general. Radiopacity is how compatible it is with imaging. Thermal stability, inflation and deflation responses. So this is when you have pressure systems often used for like balloons. So you can have a catheter, small hole in a balloon system, and then burst resistance kind of fits into that as well. So these are functional requirements, and as mentioned, you want to establish which ones are key to your application and then be able to change these design variables around it. So the key design variables to focus are wall thickness, and specifically you want to have an even wall thickness as possible. Inner diameter, this in general is meant for lumens. Nominal thickness, this is what I mentioned with wall thickness, these tie hand in hand. Lubricity, reflowability, this is a thermal property. As most of the catheters are made from thermoplastics, this is the ability to either change the shape or to combine it with others, and I'll cover it a bit in a second. Adhesion, mostly with glue, sometimes with heat. Durometer, function of stiffness, of course, and then elongation under tensile load. So to dive a bit deeper, wall thickness just means you want, as a general rule, this nominal wall thickness to be the same, even as geometry increases in complexity, which we'll cover in a further slide. Inner diameter, again, this is just driven by your application, and you want to play with that with relation to this nominal wall thickness. You can get quite small catheters, which means that there's a range of nominal wall thicknesses that will be acceptable. The reflowability is an interesting one to cover. So often you have a catheter, and this is showing the outer diameter. And if it's a thermoplastic, you're able to actually join it to another catheter using heat shrink. FEP is a common one. That's a type of heat shrink. And you're able to join these and create a rigid bond. That's one example of a reflow process. Another example is you can actually tip the end of it onto a component, if you will, using that same heat shrink. So reflowability is really just being able to use high heat and change the geometry. Adhesion, looking on the other side here at the orange, say I wanted to glue here and here, just making sure it's compatible with this orange piece and a glue of choice. UV adhesive is a common one used. UV. And then I think the next two are more self-explanatory. Another big design variable and a driving complexity factor after material is going to be cross-sectional area. So there are multiple different types. First, let's start with single lumen. This is a typical pipe style configuration, right? So single lumen has one inner lumen. Multi-lumen starts to get more interesting. So you can have multiple inner lumens, and now you see the wall thicknesses start varying a lot more, which starts getting interesting. You can also have non-circular profiles, and you can see up here at the top right some examples. So you can have, you know, a slot shape, but also the lumens can be non-circular, as shown here. And that's a nice trick to sometimes keep the wall thickness the same. So looking at both of those really quick, like a common multi-lumen configuration, if you're not going to have one internal lumen, is to say, for example, have 4 equally sized. Here, the important thing is that this wall thickness with relation to the thickest, so here with relation to the thinnest here, all those have to be considered. And a very common way of drawing this in a CAD software is to draw your lumen and then to draw concentric circles and try to get the most even wall thickness possible. I'm not sure I can do it hand drawn, but there you go. And then you would draw this exterior wall, so just like this. And so you would still have thicker areas since I drew a 3 lumen, but here you can see this thickness will be the same, this thickness will be the same, and this thickness will be the same. Okay, non-circular profiles. So looking at that real quick, another common thing that's done, you'll see, is profiles such as this. So there are multiple different ways to create these profiles. Now, it is worth noting that in the manufacturing process, often they'll put what's called a mandrel, and that is an internal component through this extrusion while it's being pulled. And so sometimes maintaining these circular profiles is going to be a lot cheaper for manufacturing. Speaking of which, let's talk about the manufacturing process. So this is a die extrusion process. So here you have the extruder with the material while it's hot, right? And you're pushing it through the head of a die here. Then it's being cooled and you're pulling it and you're cutting it to length. This is sometimes done in the same machine, sometimes done manually, but I would say this is almost like a secondary process. So you have cut and you have extrusion. At high volume, this is automated, but at low volume, when you're prototyping, oftentimes, as I mentioned, they will actually extrude the material in blue and then have a mandrel of PTFE usually, stainless steel covered PTFE, and they will pull the extrusion through while this mandrel's inside. Then a secondary step is they will remove the mandrel. And so that's why sometimes that cross-sectional area, it's a lot nicer to have cylinders because these are common off-the-shelf mandrels. And then you pull the mandrel, as I mentioned, and get your extrusion. The cutting is often done second times, and there's really no restriction on length. It's much simpler to do length cutting, and really what you're focusing on is the cross-sectional geometry when you're designing for extrusions. So this is the overall process. It's worth noting it's similar to injection molding in that you have to get custom tooling done. However, it is substantially cheaper. Injection molding is also used for certain shorter catheters. However, the vast majority of them are extrusion and then secondary operations, which is what we're going to focus on today. So kind of as mentioned, multiple channels can be created in a single extrusion process. It's useful for different subsystems, meaning in the function of the device, you can have different subsystems operating within the same catheter, and they're separated really nicely through multiple lumens. So just to draw, you can have 1 and 2. From personal experience, you need to be careful, especially with lubricity here. You can really develop some friction, but it is super nice. And geometry is often dependent on how variable the wall thickness is. Like even an example being right here, you can see most of the tolerance was concentrated on the inner lumens, but with relation to the outer diameter, it's obvious they didn't care. So yeah, covering some common materials that are used. Silicone is used, some kind of facts about it. Range of durometers, it's hydrophobic, it's sort of a Foley catheter standard. It's very difficult to bond, especially with adhesive. So often is done in secondary manufacturing processes versus during assembly. Urethanes, there's a lot of chemical compatibility. It's bioinert, and it's great for short-term use. And then nylon and PVC, it's resistant to kinking, good reflowability. Nylon does absorb moisture, which is a con to consider. The other thing is sterilizing. There's sterilization concerns with gamma. So the two major forms of sterilization for medical devices are ETO, ethylene oxide, and then gamma. Gamma is a type of radiation. ETO is a steam chamber, essentially. So gamma will turn nylon or PVC, it will turn the color brown, essentially. So you want to make sure you have the right strain. Some other common materials used are Pebax. But yeah, these are some common materials. There are also a range of materials used. So it's difficult to come with a concrete list. A nice starting point when you're making medical devices, usually you have a precedent device you're looking at, and looking at their material oftentimes can help narrow it down, as well as using common material selection strategies. So right now we've only been talking about catheters as a tube. And so now we're going to start introducing some of the additional complexity to these tubes. As I'm sure you know, in medical devices, oftentimes you can have great complexity. It's not just a tube. So one of the things that can be done is laser cut hypotubes. And so that's shown here on the left. And they will actually put this laser cut hypotube, shown in gray, with an extrusion on top of it, where it acts almost like a mandrel, and this will allow either for flexibility or, in this case, for angulation. So what they actually will do is these red dots here, they'll run angulation wires down, and then due to this laser cut, this is able to turn in multiple directions. So that's one example of additional complexity. Another thing for reinforcement is they'll actually put braided stainless steel wires, shown on the right here. This is for kink resistance. As well as, just strength. So there's a variety of inserts, if you will.